Good morning, good afternoon, good evening, wherever you are. Thanks for finding time to attend this webinar. This is our International Geoenvironmental Engineering webinar series. We have been meeting every Thursday. And as you have been seeing, we are covering a lot of different topics, and all these topics are extremely useful. Even, if you're a student or faculty or practicing professional. So hopefully, you take advantage of these webinar series, and also invite anybody who would be interested in these webinars. So just a reminder, many of you already know, we had a successful 2021 webinar series. All the recordings are available on YouTube channel. I will put this YouTube channel link in the chat box during the lecture, so you will have access to that. And then I thought we are all, done with online webinars, so I didn't want to, arrange new ones early this year. But apparently, a lot of people really like these webinars, especially people, in remote areas, and also people who cannot attend the conferences. So they really like these webinars. So as a result, we started late. So we have arranged these webinars. As you see, we have excellent 8 webinars during the months of October to early December. And we had 3 webinars already. So this is our 4th webinar. And you can find more information about these webinars at the link that I shown you on this slide. And today's webinar, as of this morning, we have 610 registrants. So it's a lot of good response. Please mute your mic and switch off your video. Type your questions in the chat box at any time during the presentation. And make sure you select our presenter's name. He is a co-host, so send the questions directly to him. So our presenter will answer at the end of the presentation. Thanks again for everyone for joining this webinar. So regarding today's topic is Beyond Geophysics, Electromagnetic Waves for Geoenvironmental Engineering. Our presenter today is Dr. Arvin Farid. Let me have a brief bio. Dr. Arvin Farid is a professor in the Civil Engineering Department at Boise State University in USA. He is also the director of the SEnS-GPS, which is a NSF-sponsored project, and he is also the director of Clean Soils Research Lab. Arvin received his PhD from Northeastern University in Boston. During his PhD, he was an associate research scientist at the Gordon Census Center for Subsurface and Imaging Systems. It's headquartered at Northeastern University. He received his BSc and MSc from Shiraz University in Iran. His educational and research backgrounds are in civil and electrical engineering, as well as geophysics, which is the topic of, topic of interest to a lot of people who work in geophysics. His research areas include subsurface sensing and sensor development, multi-physics, multi-scale numerical modeling, wildfires, geoenvironmental impacts, remediation, recycling and reuse of industrial byproducts, and liquefaction mitigation. So he has a very broad research interest. He has more than 60 publications on these topics. Dr. Farid has received research funding over $4 million from the National Science Foundation, National Aeronautics and Space Administration, NASA, U.S. Army Corps of Engineers, Idaho Transportation Department, and various industries. So with this brief introduction, I want to thank Arvin. He is my good friend, for agreeing to give this webinar. And I want to thank everyone for taking time to attend this webinar. We enjoy the webinar. So thank you very much. So I will stop sharing the screen. I will request Arvin to share the screen and start presentation.
Thanks, Krishna, for the kind introduction. Do you see my screen in the slideshow mode? Okay. Today, I'm going to talk about electromagnetic waves and how they could be used for various purposes in geoenvironmental applications, as well as geotechnical. And the topic, or I call this Beyond Geophysics. However, I'll start with a relatively briefer discussion on geophysical aspects and the traditional use of electromagnetic waves through geophysics, and then move on to the more novel approach, which is what we have pioneered in the past decade or so. Traditionally, when you talk about geophysics, you're trying to use a type of wave to detect, monitor, or characterize something within subsurface. Subsurface, be it human body, soil, or within any object. And how the way waves work is basically you try to discriminate a or multiple properties between an anomaly and the background that the anomaly is surrounded with. And because the propagation of any wave is governed by properties of the medium they propagate through. When we talk about electromagnetic waves, in this case, in this example that I'm going to show you, we are discriminating against electrical properties, because electromagnetic wave propagation is governed by the magnetic and electrical properties. And as long as there's a contrast between the anomaly and the background that's hidden in a background, in terms of either electric or magnetic or both properties, you could find the anomaly within the background. Now, I mentioned, and by the way, since we're talking about waves, everything could be discussed in time domain or frequency domain. And by everything, I mean numerical models as well as experimental or field experiments, laboratory or field experiments. And we have to use inversion and image algorithms to be able to create images of this anomaly within that background. The two most popular formats of using electromagnetic waves are, one is GPR, or ground penetrating radar, which is a surface refraction method, where you have, in this case, you have an antenna shown in yellow, a transmitting antenna, and then the waves are emitted off of the transmitter, go into the ground, in this case, reflected off of the, let's say, groundwater or whatever else you're trying to detect, and bounce back, and the receiver will pick them up, and that's how a surface refraction method works. Now, you could have cross borehole methods when you have multiple boreholes, and you could have a transmitter and receiver antennas, let's say the transmitter on the left, and then waves propagate out, and the anomaly with contrasting properties would be detected, and you could have multiple receivers. This is very similar to a CAT scan that you could have performed at a hospital. Now, obviously, if you look at the literature, these are some famous names who have tried to discriminate and characterize or detect anomalies, or characterize soil in terms of some properties, moisture content, soil or water salinity, and so on and so forth, mineralogy. And there are some famous names and some good friends among these. Now, I mentioned dielectric properties, which are dispersive properties of a medium. And by dispersive, I mean they vary with frequency. Hence, if you pick different frequencies, you could detect different objects. So electric properties are basically two main properties: dielectric permittivity and electric conductivity. And we're not talking about the magnetic properties at the moment. Dielectric property or dielectric permittivity is a complex variable. It has a real part and an imaginary part. So here, epsilon, the asterisk means it's complex. Epsilon is the dielectric permittivity of your medium. We typically normalize it to the dielectric permittivity of the vacuum. which is 8.852 times 10 to the negative 12. The ratio is called relative dielectric permittivity, complex relative dielectric permittivity, or this kappa asterisk. And complex dielectric permittivity, since it's complex, it has a real part and it has an imaginary part. The real part and the imaginary part itself is sort of related to electric conductivity as well, and the frequency of the wave that is propagating. And because of this relation, we can define something called the loss tangent, which shows how lossy the material is, how energy absorbing the material is. For example, water is very lossy, which is why it absorbs energy that comes off of electromagnetic waves, which is how microwave ovens work. If you put a cup of water or coffee in a microwave oven, it would warm up for that specific reason. Now, let's look at some typical properties of some material. Up top, you see PCE, which is a type of DNAPL, dense non-aqueous phase liquid. You see water and different types of soils. And if you look at their dielectric constant, otherwise known as relative dielectric permittivity, the real part, you could see that for water, we have a dielectric constant of close to 80, while for, let's say, for dry sand, it's only 3, or for PCE, it's only 2.28. And the same contrast exists for the electric conductivity. And if you have a contrast, that means chances are you could detect an object. Now, how do we detect an object? We typically need a forward model for detection and an inverse model. What do I mean by a forward model? If you have a known excitation, an antenna that sends out a signal that we know how it looks like, be it sinusoidal or a Gaussian signal, a pulse, then if we have a known medium, our forward model would numerically simulate this propagation and would tell us what the receiving signal would look like. It would compute the received signal. That's called the forward model. And any forward model, which is a numerical model, would be, as any other software, would be garbage in, garbage out, unless you give good input and the model is validated and you get good output. And what do I mean by validation? This model can be created in time domain or frequency domain, and you got to have an experiment in either time domain or frequency domain, and you got to compare the results and validate the results, validate your numerical model. In other words, you create a forward model, then you experimentally and numerically measure the field, the electric field in this case. You compare them. If the difference, if they resemble each other and the difference is negligible, that means your forward model is validated. The key is this: your numerical model could be in time domain or frequency domain. Your experimental work could be in time domain or frequency domain. That gives you more tools to be able to work more flexibly. Now, let me show you some examples of forward models. In time domain, forward models are basically numerical codes that solve Maxwell's equations. These are the 4 famous partial differential equations that describe Maxwell's put together. Not all developed by himself. And these are the constitutive relations between the properties of the medium, the electric field E, and the electric displacement D, magnetic field H, magnetic displacement. And because of the complexity of this and the fact that there's some correlation between electric and magnetic fields in this experiment, in this numerical model that we prepared years ago, we used a specific type of cell or mesh to discretize the domain. And for the electric conductivity, we had to consider that complex as well. And it's an impedance-based model. We did that. These are some properties that go into that model. And then let me show you some of the results and later on. Now, what do I mean by inverse models? By inverse model, that means I have a medium that I don't know what it is and what it contains. I have a signal that I transmit out, which is a very known signal. Experimentally, I send it out. I know what it is. I don't know my medium. I measure the received signal using my receiving antenna, and I have a good handle of what that received signal is. The goal of an inverse model is to invert your forward model and figure out what your medium is, and hopefully even create an image of your medium. Now, how can we do that? If we could invert our forward model, if it was a simple model, great, we'd do that. That would be easy. But in general, you cannot. So what we employ is different schemes. One is an optimization scheme. What do I mean by an optimization scheme? This is basically to solve this inverse problem. You experimentally measured your received signal. You assume some properties of the spatial distribution of properties of the medium, and then you simulate and compute using your numerical forward model what the received signal would look like. Then you look at the difference between your received signal from your simulation, from your forward model, and your experiment. And this difference is the cost function for our optimization scheme. If the cost function is large, we have to go back and optimize, modify our assumptions, run the simulation again, find the simulated signals, go back and compare, find the cost function again and again and again, and this could be repeated. And finally, if the cost function is minimal, that means our assumptions about the medium have been correct, which means our inverse problem has been solved. We have created an image of the medium. So let me show you some examples of forward models. In here, we have a medium of soil shown in brown. We have a monopole antenna at the center, this vertical probe. We have a Polluted apple there, and we could simulate this and look at different slices, vertical or horizontal, and see how the wave propagates. First, another concept used in geophysics. On the right, I'm sorry, on the left, I have a vertical slice of how waves propagate when the soil is clean, there's nothing in it. And if you click on it, you see the waves travel down the probe and into the medium. Everything is symmetric and perfectly symmetric, no object, no anomaly. Now, if I look at the horizontal slice like this, this shows the top view. The center is that vertical probe, and then the soil is not clean. There's an object in there hidden on the right side. And when the wave comes out, it gets scattered by that object, meaning that beautiful symmetric pattern gets all messed up. The first one on the left was called the incident field. This one is called a total field. And if I numerically subtract the two, even for an experiment or a field lab or field experiment, then I get to the difference, which we call the scattered field. And if you look at it, mathematically, it looks like the scattered field is coming off of the object, which is why we call it the signature of the object. So this is basically how a forward model could simulate an object in there. And the forward models, that was a time domain forward model. This is a frequency domain forward model, which is a much easier equation to solve relatively, Helmholtz equation. There's no time in there. And there are different approaches. This is another model we created. Don't want to get into the details of that. We use the Green's function. You could basically solve this and find the results in frequency domain. Both are feasible. The time domain one is very time consuming to solve. The frequency domain is much faster, but that just gives you snapshots, doesn't give you the entire answer. Experimentally, it's very complicated. It could be done in frequency domain or time domain. What you have is you have two antennas again, a transmitter and a receiver. Waves go off of the transmitter into the receiver. And measuring the travel time of the wave is a little difficult, more noisy, so so time domain experiments could be a little more challenging, but sometimes people resort to to frequency domain measurements, which they don't care about the time. It's just they send the signal out, they receive it somewhere else. If it goes from antenna 1 to antenna 2, we call it S21. If it goes from antenna 1 out and then collected back by antenna 1, meaning our antenna is both a transmitter and receiver, the bottom image, we call it S11, where the antenna is a transceiver, not a transmitter or a receiver. And the ratio between the received signal to the transmitted signal in a dB scale is called the response. And you could measure that across various frequencies. And these various, and then there are challenges with the antenna, how to couple them well with a medium and so on. This is an antenna that we sort of invented that would solve some of those challenges. And the problem with these measurements is, like any other, here you see an antenna for a receiver and a transmitter. The problem is when you have these antennas, any measurement that you collect would be distorted by your sensor. Any measurement is messed up and distorted by the sensor. Imagine you're trying to measure the flow in a river. If you put a flow meter into that river, you're distorting the flow measurements. You're distorting the flow of the river. So any measurement impacts the parameter that you're trying to measure. And we gotta somehow take care of that. And this is a scheme that we used to mathematically basically extract out of these S21 and S11 measurements, something called the channel transfer function, which is the pure measurement due to S21 measurement of the soil, not what's impacted by the receiver and transmitter. These are some challenges that geophysicists need to deal with. And then you could apply that CTF to your measurements and your numerical forward model in a dash, using the dashed line here, and all those simulations sort of start to agree. And then experiments that are in frequency domain using fast Fourier transform could be converted. And from a frequency domain measurement, like the one in the previous slide, I can find the travel time in here. Basically, I can send the signal out, and the signal is in time domain, convert it to frequency domain, and multiply it by your channel transfer function. Then by inverse FFT, take it back, and the results would be in frequency domain. Then you apply inverse FFT to find your received signal in time domain, and figure out that if the signal was sent at 1,000 picosecond, you can find out that it's coming back at 6,000 picosecond. So that's how this experimental frequency domain results could be converted to a time domain experimental results. And then they could be used with an optimization scheme to create an image that looks like a CT scan of an object that we had hidden over here. This was an overall relatively brief discussion on fundamentals of how geophysicists detect objects and what geophysicists do day in and day out. Now go to this novel approach that we pioneered within our research group over the past decade. Previously, I told you that when an electromagnetic waves or any other wave propagates through a medium, it would be scattered by the medium. It would be impacted by the medium. And that's by measuring that scattered field, we could figure out what's hidden in the medium. Now, according to Newton, for every action, there's a reaction. So if the waves are scattered by the medium might be impacted by the waves as well. That's the whole thought process we had. How may help us use electromagnetic waves for remediation? You've probably seen other folks use electric current for remediation. Krishna is one of the pioneers in that field with electrokinetics. We try to use electromagnetic waves for remediation. And if you look at a typical contaminated solar groundwater problem, there are ex situ methods like dig and treat, pump and treat. There are in situ methods like air sparging. A lot of methods have been used, and some of these methods are pretty slow. There's natural volatilization that we're trying to stimulate all the time. And there's natural biodegradation that exists. And we could sort of, if we could stimulate them, they would be faster, more productive for our purpose. There's air sparging that has been used in situ, and soil vapor extraction, and so on and so forth. All these methods have their flaws. They're slow, and we'll talk about air sparging in more details. If they could be stimulated, or if we could find a better method to remove the contaminants, that would be wonderful. And some research in the past, people have used electric current in the DC form. We call it electrokinetics to remove contaminants. AC has been used to remove contaminants. Both AC and DC generate some heat, and DC could change the pH of the medium, which could impact the macrobial life that could help with biodegradation. So we thought with electromagnetic waves, we could come up with an approach that would not generate heat and would not change the pH and still remove contaminants. Why did I think we would not generate heat while your microwave oven generates heat? If you pick the right frequency, you should be able to move things around without generating any heat. Why? If you remember that famous parameter epsilon, or dielectric permittivity, is complex, has so many different components in there, and we can work with a frequency and pick the right frequency so we don't generate heat, yet we generate some movement in the medium. If I look at this kappa prime and kappa double prime here, which in this case are shown as epsilon prime and epsilon double prime on the vertical axis, and you look at them across frequency on the horizontal axis, these parameters relax and drop at different levels. In other words, when an electromagnetic wave is launched into a medium, particles that are charged or dipolar, meaning they have a positive and negative pole, start oscillating within the medium. The faster they oscillate, the more particles that they oscillate, that epsilon prime would be larger, and epsilon double prime. But as the frequency goes up in this direction, particles that are large and heavy stop oscillating because they cannot, because of their inertia. So they start relaxing. So initially you start seeing that ions that are large start relaxing. Actually, first bound water starts relaxing. Ions start relaxing, bound water starts relaxing. Then right around here, the free water molecules start relaxing, then atoms start relaxing, and even electrons start relaxing at a very high frequency. And when they start relaxing, they stop fluctuating, they will not absorb energy, and they allow the wave to go through, which is why a very high frequency X-ray can go through everything pretty much. But some waves at 10 to the 3 hertz or megahertz or kilohertz will not go through a lot of medium. So basically that absorption, if we pick the right frequency, we might not deal with that lossiness and absorption and heat generation. So that's basically what we're trying to do. Now, we could move contaminants around, we could enhance and control the zone of influence of air sparging, and so on and so forth. That's the whole basic behind what we thought would be possible. The problem is these experiments have to be run at the lab scale. We wanted to run a controlled experiment, so we had to run them within cavities. Cavities are basically boxes made of metal, and if you create a cavity, depending on the wavelength of the wave that you launch into the cavity, you could create these different radiation patterns. And based on these radiation patterns, we could create different flow patterns, which is what we were trying to do to show that the electromagnetic waves could be used for remediation. So this is a setup you could see. It's a box made of plexiglass you could see through, but we covered the box with films that are electrically conductive, like metal, but they're transparent. And then we could fill this with water or soil, and then we could inject contaminants into these little cups here. And then using this antenna up here, we could launch electromagnetic waves of different patterns and see if we could move the contaminants around. And we didn't use a DNAPL, we used the DNAPL surrogate, which was basically similar to DNAPLs, denser than water, more viscous than water. And you need a lot of tools to do that. I don't want to get into the details. You've got to create a signal, use an amplifier, amplify the signal. You need a transmitter and receiver, and so on and so forth. Again, I don't want to get into the details. Two different types of antennas could be used, either a loop antenna that magnetically excites this box, which we call a resonant cavity, or we could use a monopole antenna. And we realized at the end of the research that the process that controls the flow of the or the movement that we induced onto the contaminants, the process is a process called dielectrophoresis, let's call it, which is the equivalent of electrophoresis, but for electromagnetic waves. And the equation that controls dielectrophoresis is this: the force that's applied on the particles of that contaminants are proportional to the dielectric permittivity of the particles of the contaminant and the water or soil background. It depends on the gradient of electric field we have in there, and it depends on the size of the molecules of the contaminants. This was shown to work for different size particles in manufacturing, but not for the size of molecules of contaminants we are talking about. And that's what we discovered. And let me show you that we proved that actually this worked, this dielectrophoretic force worked. So we created this box, we put the antenna at different locations, created different patterns, and with soil, with water, and we, again, back to what I was saying, we created numerical models of the electric field. We created experimental models, we validated that numerical model, and then we figured out what this field would look like, and we knew how the contaminants would move. And let me show you this example that shows how it worked. This is a box. At the center, we have this little cup full of DNAPL surrogates. Since DNAPLs are heavier than water, if there was no electromagnetic waves, the DNAPL would diffuse out and then sink down. And then this bottom half would look all green, as you can see. The top would look clean. That's what happens in nature when you have DNAPL sinking into the ground. Now, here we applied an electromagnetic field at 65 megahertz with 10 watts. A little bit of dye was coming off of this. Nothing was going down. A little bit of dye was coming off of this to the surface. We increased the power to 20 watts. More dye is coming out, as you can see. We increased it to 30 watts. A lot more dye. You could sit and watch this entire dye coming to the surface and could be extracted later. Then we applied 75 megahertz. You could sit days or weeks and no contaminant would get out of the dye, out of that little cup. Why? Why is it that at 65 megahertz we can extract the contaminants that would naturally sink down up to the surface, and at 75 megahertz we could trap them right where the spill is? Think of it as if you, for the first case, A, B, C, and D, we try to extract some contaminants out of water or soil. For case E, we try to contain them temporarily or permanently. Why would it work? Because of the dielectrophoretic force. If you look at the field on the left, 65 megahertz, this is what the field would look like. This is the direction of this is what the field would look like, and this is the direction of the dielectrophoretic force. That's why the dye goes up. And if you look at on the right, for 75 megahertz, this is the field, this is the direction of the electric force. It would squeeze everything to hold and contain it. So that proved that this method would work. And the heat that was generated in the setup was below 1.6 degrees Celsius, caused below 1.6 degrees Celsius temperature change, which is wonderful for microbial life that exists there. There's no pH change, obviously, either. And we studied that and showed that at different frequencies, the amount of contaminant that we could extract would be proportional to the power. The horizontal axis is the power, the vertical axis is the amount of dye that we extracted. And at the blue line is 65 megahertz. The 75 megahertz case is a red line, flat, no contaminants gets out of this cup. And we studied, we even controlled the width or shape of that plume of contaminants that would go up. On the horizontal axis, you see the width of the plume. On the vertical axis, you see the vertical depth. And that basically shows the profile of the contaminants that would go up. And we tried it for different forms. And for example, in this case, the cup is located here. Dielectrophoretic force should be downward to the right. And you see the dye is going to the right. In this figure, the two cups located, cup 1 and cup 2, the force should be in these directions. And you see the dyes are going in that direction. So that proved that this method works. Let me show you another example that shows this method works. We looked at air sparging. And if you look at air sparging is one of the most popular methods for removal of contaminants. When drinking water is contaminated, we could use with contaminants that are harmful, as opposed to these ex situ methods, a lot of people use air sparging. Why? Because air sparging could vaporize, volatilize the VOCs, volatile organic compounds of contaminants. If you have a contaminant within the soil, if the natural volatilization would eventually help over a long time, would eventually help vaporize, volatilize VOCs, and they come out of the soil. And you could extract them, or they could go into the atmosphere. Whatever is rest would be biodegraded. The part that's not volatile would be biodegraded through bioremediation, biodegradation or bioremediation. Now, what air sparging does is this. If I have contaminants within the vadose zone, this area, obviously there's air, contaminants are exposed, they're volatilized and they get out. The VOCs at least get out. But if the contaminants like are within the saturated zone here, there's no air. So they're not going to vaporize, volatilize. Hence, you never get rid of the VOCs. What air sparging does is you drill a hole, put a pump in there, pump air in there, and as the air is introduced into the soil, it would volatilize the VOCs. And then using methods, this is called air sparging. And using methods called vapor extraction, you could extract whatever vaporized, volatilized VOCs that you have got into the vadose zone. That's basically air sparging used in conjunction with soil vapor extraction. The problem with air sparging is this. Imagine if I have a cup that's empty, I put a straw in there and I start blowing air into the cup, the air freely goes everywhere. But if the cup is full of water and if I put a straw into the water and start blowing air, initially the air would not go out. I have to keep increasing pressure, increase, and all of a sudden a bubble forms and it goes to the surface. It doesn't spread out into the cup. So that is a problem. That means the air sparging may not clean up the entire cup. Now imagine this is a big bubble that comes out. If I have soil, this big bubble would turn into small bubbles or channels, which we call them preferential, these channels that are formed, and the whole phenomenon is called channel formation. And these channels or small bubbles are formed in a zone, which we call zone of influence. The problem is these channels, the very first time that you increase your pressure, soil particles are moved, these channels are formed, the air within the channels would probably clean up some area, but the problem is the cleanup area is only surrounding those channels, but the channels are formed preferentially, and even if and it would not clean everywhere. So the solution that the industry has found is a method called pulsation. What they do is they run this air sponging, they start the system, channels are formed, they clean up the soil, then let's say they run it for a month, they shut it off. And if they started right away, the channels are formed right where they had formed before, because those are preferential paths that are created. Now, they have to wait. They wait probably 6 months, 5 months, 4 months. They start the system again, hoping that the channels are formed elsewhere, which good luck. So the channels are always formed where they initially formed. The cleanup may or may not be complete. So we thought that, hey, using that dielectric, unlike electrokinetics that only moves charged particles, dielectrokinetic, call it, and I'm trying to coin that term, who can move charged particles, neutral polar particles like water, neutral non-polar particles like bean apples. We showed that. So air is neutral non-polar. Why not try to move air particles around and basically sweep this zone of influence and these channels around into soil and clean up the entire medium? That was using electromagnetic waves. That was the whole purpose of this work that we did. So basically, our goal was to change the shape of this zone of influence. Also, to increase or change this radius of influence, which is basically the top view radius of where the air gets out. Because air gets out at the bottom, but creates a cone, which we call zone of influence. The radius of this zone of influence is called Ri. So the whole point is use electromagnetic waves to come up with a method better than pulsation, because pulsation is costly. You deploy your air sponging equipment, you run it for a month, you have to keep it off for 6 months. What the heck? That's costly. So we tried to see if we could enhance air sponging. Before we did that, we had to understand how air pressure impacts the zone of influence of air sponging, then figure out how electromagnetic waves could influence the zone of influence. I think I'm at 45 minutes. I'll go a little faster to cover all of this. So we created different setups. Here we have a setup with saturated zone, vadose zone, air, another setup with only saturated and vadose zone, no air, another one with all saturated zone. This is another cavity, resonant cavity we created. We put the loop antenna there. We put the pump at the center. And then we wanted to look at multiple, these are our configurations, the 3 configurations that we created. And then we wanted to test 2 different things. What happens if we vary the initial air pressure that we apply? How would it impact the zone of influence? And then when the zone of influence of air sponging is formed, what happens if we increase the air pressure? And not only we tried this with air, we tried it with electromagnetic waves, meaning that what happens if before air sponging is run, we launch electromagnetic waves, and at variable electromagnetic power, how is the zone of influence of air sponging impacted? And what happens after the zone of influence of air sponging is formed if I increase the power of electromagnetic waves? So that's the whole purpose. So the first test was without applying electromagnetic waves. We vary the initial air pressure and measure the zone of influence, for all cases. Then after the zone of influence is created, we increase the air pressure and see if the zone of influence is created by the further increase in air pressure. So call the left case initial air pressure impact, the right one further increase in air pressure impact after the flow is formed. And we do that the same with electromagnetic waves. We form air channels, then launch electromagnetic waves and increase the power, vary the power, see how it works. Then before the air sponging is running, we launch electromagnetic waves at various powers and create the air sponging zone of influence and see how it's impacted. We noticed that this figure shows the radius of influence of that air sponging zone on the vertical axis and shows the impact of initial air injection pressure, meaning that if I start my system at 10 kPa or 20 kPa or 40 kPa or 60 kPa, the zone of influence for those two configurations, 1 and 2, it showed that the radius of influence is proportional to the initial air injection pressure. Obviously, for configuration 2, we have a soil, dry soil, or sitting on top of that saturated soil that sort of pushes the air outer, and the radius of influence would be larger. This one shows that when the channels are formed at whatever initial pressure, you could further increase the air pressure to the right on the horizontal axis, and the radius of influence would not change at all. So this is what we saw with air sponging. You pick the initial pressure, you turn it up, you create the zone of influence, you can increase the pressure as much as you want, it wouldn't impact anything. So initial air pressure is more important. Then we thought that could mean that before the air sponging starts, we gotta launch electromagnetic waves, not after air sponging has started, that airflow pattern is formed. So we created the same setup, the same cavity, this time is longer. This is a pump that we pump air in there. The antenna is right here. And we did very similar things. So here you see the top view of that box that I was showing. This top view is shown right here. On top, you see the soil. The pump is at the center. We pump the air, and you see this zone of influence that is formed here. It's circular, symmetric, because air is symmetric. The soil was homogeneous. And you could look at this radius of influence of this. On the right, you see that electromagnetic waves were launched before air sponging had started, and this pattern of zone of influence was formed. And you could measure the larger or smaller radii in here. So we could impact it. And why is this lip-shaped form? Why is electromagnetic waves forming this or changing the zone of influence in this way? The other thing we studied is on the horizontal axis, you see the initial EM power before air sponging is turned on, and here you see the area of zone of influence. With higher electromagnetic wave power, we could increase the area and the radius of zone of influence by roughly 25% here. So not only we can change the shape, we could increase the size. And this is before the system is turned on. You have to launch the electromagnetic waves. And by the way, if the channels are formed, good luck. No air pressure, no electromagnetic waves would do anything for you. The other thing we did is we swapped the location of the antenna to see how it impacts. By the way, that lip-shaped form, if you look at this box, we simulated the electric field. We figured out what it would look like. We figured out what the dielectric force would look like. And if you look at the top view, the center is the pipe. The pipe is right here. The dielectric force should push the air to turn from a circle into a lip, which is why this lip-shaped zone of influence is created. Which means if we change the electromagnetic wave pattern, we could control the shape of the zone of influence, not only the size of the zone of influence. And then we put the antenna off center and moved it to the right and left to see if everything is controlled differently. And we realized that when we move the antenna or the pump to different location, I'll show you the results. And if, let's say, the pump is at some location, if I flip and move the antenna to the other side, a symmetric shape could be created for a different frequency. So meaning that it's electromagnetic waves controlling the air sponging pattern. And this is pretty much what we could do. The temperature change in this case was smaller than 1 degree Celsius. We could move. We tried this. I don't have the results shown here. We tried this using soil, saturated soil, using water as well. And by the way, one thing that I don't have in this, we're still studying, is when we use electromagnetic waves, there are other unforeseen impacts. Any solution that us human beings create could have some side effects that we might not be careful about. So we looked at these impacts and we realized that the electromagnetic waves not only impact the flow of air or contaminants, but also they impact the hydraulic conductivity of the soil. Interestingly, we realized that depending on clay or silt or sand or gravel, the type of soil we're dealing with, the hydraulic conductivity could be increased or decreased. And that's a function of frequency and power. Also, we realized the microbial life in there could be impacted. If the microbes are like yeast that are used for brew fermentation, that are very temperature sensitive, even 1 degree Celsius could stop them from growing. But if the microbes are not that temperature sensitive, obviously, then you could stimulate their growth when you want them and enhance by remediation, or you could stop their growth when you don't want them, which is like autoclaving using electromagnetic waves. So all of those are feasible. But the good thing is we could control this temperature change within a couple of degrees Celsius, while in other methods, such as using AC or DC current, that could be up to 10, 20, 30, 40, 50 degrees Celsius or 100 degrees Celsius. You could even boil water with DC or AC. Electromagnetic wave, and we don't control probably. With electromagnetic waves, I could boil water or I could even keep the temperature constant. With that, I'd like to acknowledge NSF for funding that project and some of the co-authors. And thanks for your attention. And I'll see if I could try to answer your questions.
Yeah, thank you. Thank you, Arvin. Very, comprehensive presentation. And so I hope, your presentation has given a lot of good ideas on, using some innovative techniques to enhance remediation, maybe, a lot of applications.